Welcome back. Fancy meeting you here. Okay, here's my next theorem that says if H is a subspace of vector V, any linearly independent set in H can be expanded to be a basis for H. And so if necessary, we might not need to expand it. But remember that I have to, in order for it to be a basis, I have to have those two qualifications that I got to meet, right? It needs to be the span of those elements need to equal H, and the elements are all linearly independent. So just having a couple of linear independent pieces in my set doesn't necessarily mean that the span of those two pieces is going to give me all of H. But if I can add to it, then I can get a basis for H. And that if H is a subspace of the vector space V, that the dimension of H is always going to be less than or equal to the dimension of V. So here's sort of a more concrete example of this. So here's my subspace defined by x0, the vectors of x0, where x is some element in the real number system. So this is a subspace of R2. Hopefully you can see, though, that this will not build, so will not build all of R2, right? But if I just pick some element of this, and hopefully it's easy to see that if I just take the element 1, 0, that all I need, and another way to think about this is this is the x-axis, right? So any linear combination of 1, 0, right? If I take a times 1, 0, I'm going to get anything on the x-axis. So the span of 1, 0 is equal to H, right? Hopefully you agree with that, right? Oh, here, we'll pull the X out. You ready? That's better. So the span of that is equal to H, and the basis for H here, so that means that our basis, and 1, 0 is going to automatically be linearly independent with itself, right? There's nothing else to be dependent with. So the basis for H is the set 1, 0, which has a dimension of 2. Now R2, because we already talked about how however many elements, so remember we talked about the dimension for all of the R3 sets was 3. Hopefully you understand, or it follows that the dimension of R2 would be 2. So the maximum number of elements that I need to define all of R2 is 2. So in other words, if I add to H, so if I add 0, 1 to H, which now turns it into a very different variable. So if I add that H, I'm no longer in H. So I already have a basis for H. But if I add that to the set, so we won't call it H anymore, we'll add it to the set 0, 1, 1, 0. It doesn't matter the order that we list those things in a set. Set's not ordered in any particular way. That those two elements, this has a dimension of 2, and hopefully you can see that this is a basis for R2. Hey, look at that. So the basis theorem says that if V is a p-dimensional vector space, any linearly independent set of exactly p elements in V is automatically a basis for V. Right? So we just showed here that the two linearly independent sets, so R2 is two-dimensional, which hopefully makes sense, right? That's the dimension, talks about how many, hey, look at that. Comes full circle. All right, so it's two-dimensional, and that one basis for R2 is 1, 0, 0, 1. Okay? But another possible basis could be something, sure, I don't know, 7, -1, and -1, -1. Right? That's another basis for R2 because they're linearly independent. I only need the two of them, but I can take any combination of those two things to get me all the other vectors in R2. But you'll see that that it's going to have exactly the number of elements as our basis is going to have exactly the number of elements as our dimension. All right, that's the thing. All right, fun fact. The dimension of the null space of A is the number of free variables in AX equals 0. All right, so remember, to find the null space, we find the solutions to AX equals 0. We represent them in parametric vector form, and then the null space, or the dimension, or the basis for the null space, we did that in the last couple examples earlier in previous sections. The dimension for the null space would be how many vectors it takes to make the basis for the null space. And it took as many vectors as there were free variables, because we use the free variables to represent our parametric vector form of our solutions. And those vectors are what make up the null space. Hope that makes sense. All right. The dimension of the column space of A is the number of pivot points, or of pivot columns in A. And hopefully that kind of makes sense, right? The dimension of column A is defined as the span of the columns of A. So that would just be list all the columns of A as the span, but we only want the linearly independent columns, and those linearly independent columns happen at the pivot columns, and the pivot columns are what's going to give us our basis, and our dimension is the number of vectors it takes to make our basis. Whew. Okay, just a reminder. So here's our lovely, lovely, wonderful definitions of null space and column space. But we're on a different page the last time I mentioned it because I got rid of some stuff that we didn't need to do. Shh, don't tell anyone. Okay, so we're going to find the null space, the dimension of the null space, and the dimension of the column space for A, which means that we need to find the basis for the null space and the basis for the column space, and we need to, which basically means we need to find the null space and the column space. There. The column space is pretty easy because all we need to do is augment A. So if we augment A and just figure out where our pivot columns are, so we don't even need to augment A all the way down for the column space. We can just we can get it to the point where we can say, hey, I have some pivots and I don't have some pivots. But I'm gonna just for funsies, why not go the whole yard? I don't know what I'm saying. 1, -2, 0, -1, 3. Again, try these out on your own. Either do the lovely, my favorite operations on your own, or you can use a calculator to do the row operations. I am a-okay with that. But as you can see here, so in this first row, here's my first pivot point. In the second row, here's my first pivot point. In the third row, I have no pivot points, which means that my pivot columns are the first column and the third column, which means that our basis for the column of A is the set of the original first column and the original third column, because those are the ones that are linearly independent of each other. -1, 2, 5, So there's my basis, which means that the dimension of the column of A, or the column space of A, is 2. Ta-da! All right. Now, we've already done most of the hard work that we need in order to figure out the null space of A. So the null space of A would be, so this was A is equal, if I take A and I augment it with the 0 matrix, vector, 0 vector, then we get this exact same vector matrix. But I have zeros over here. And what this tells us is that I have 3 free variables, which I don't actually need to know. So I guess we didn't really need to talk about the basis of the column of A. I lied. We just needed to figure out where the free variables and the pivot columns were. All right, so I have 3 free variables. Therefore, the dimension of the null space of A is 3. And I don't know if you can see what's happening here, but maybe that'll tickle your brain a little bit until I get to the next. And this idea, this 2, 3, which again, we're going to find bases for null of A and column of A. So this time we're not talking about dimensions, we're just talking about bases, and that hopefully will come up in the next section. Okay. Let's find our bases for null of A and the column of A. So again, column of A, this is the span of the columns of A, and the basis is what happens is all of these. So the basis is the columns with a pivot, or the pivot columns. Pivot. And the null of A is the vectors, or the base for the null of A is the vectors that make up the parametric vector form of the solutions of AX equals 0. Okay, once again, we're going to augment A, and it really doesn't matter. I'm going to just throw it into this one already. I'm going to augment it. We're going to come up with a lovely, am I even looking at the right one? I don't even know. We'll just, hey, I found it. Okay. I'm gonna, la-di-da-di-da. 1, 0, 1, 0, 1, 1, 0. 0, 1, negative 2, 0, 3, 0. 0, 0, 0, 1, negative 5, 0. And a lovely row of zeros. Okay. So I need to identify where my pivot columns are. So first row, hey, there's a pivot column, pivot column, pivot column. So that means that my basis for column of A is equal to the set with the first column, this guy, negative 2, 1, 3, 1. The second column, that's another pivot column, negative 5, 3, 11, 7. And the fourth guy, because that's another pivot column, 1, 7, 5. Yay! So there's our column of A basis. Now, the null A basis takes a little bit more finagling to get there, right? So now we need to write our equations. So x1 is here 1, x2, x3, x4, and x5. So we know that our free variables are x3 and x5. So x1 is negative x3 minus x5. x2 is 2 x3. Am I looking at the, no, this is the wrong matrix, isn't it? Oh no. No, we're good. I don't know. I'm feeling deja vu, but that might just be me. Did we do this already? Okay. X3 is, well, itself. x4 is 5, x5. Yeah, this is feeling real familiar. Anybody else? Did I put this in the wrong spot? Whatever, we'll keep rolling with it. x5 is, well, x5. So in terms of our vectors, our x vector is defined by the x3 variable times -1, 2, 1, 0, 0, and x5 times -1, -3, 0, 5, and 1. Right, so the column space, or the null space, so the basis for the null space of A is the set of, here we'll call this V1 and V2. Set of V1 and V2. Those are big matrices now, or vectors now, we're in them again. All right, feel like we did that once before, but maybe not. All right, that's it.